Greetings of the day. Myself, I'm Dr. R. Venkat. I'm working as an associate professor in the Department of Computer Science and Engineering. So today, I'm going to discuss the introduction about Automata and Compiler Design. Regarding Automata and Compiler Design, actually, I think previously we used to have two courses. One course is flat and another course is compiler design, that is CD. This flat is also called as theory of computation, which is TOC, and this CD in other universities it is also referred as compiler construction or language processors. I think long back they used to call this particular course as language processors, because this process any programming language. So regarding regarding flat and CD, okay, so they merged these two courses into a single course called as ACD, that is Automata and Compiler Design. In some universities, this is also called as ATCD, Automata Theory and Compiler Design, or Automata and Compiler Design. So regarding, first of all, what is flat and what is compiler design? First, I will explain this one simply, and we'll try to go in depth regarding this one. First of all, flat. Flat means formal languages and automata theory. This is also referred as TOC. Okay. So first of all, let me explain before going to discuss about what is flat and what is compiler design. Let me discuss what kind of an intuition you require to understand this particular course. So I think in 1950s, around 1950s, we have a mathematical professor, Alan Turing. He introduced a mathematical model called compiler. He introduced a mathematical model called compiler. Later, this compiler is actually implemented in the form of a program. So this is also called as software. Okay, we all from the very beginning we used to discuss, we used to refer compiler as a program or a software. So in the beginning, it is a mathematical model. In around 1950s, a mathematical professor, Alan Turing, he introduced a mathematical model called compiler. Later, in order to implement any kind of programming language, they had implemented this particular compiler in the form of a program or in the form of a software. So first of all, what is this compiler? What is this compiler means? A compiler will convert a high level language into a low level language. What is high level language? High level language means nothing but the program whatever we write with some high level constructs. When we write a program in any programming language, so that programming language, if you write a program in any programming language, that programming language can be anything. That can be C, Java, C++, Python, .NET, Scala, Pascal, Algol, Fortran, EFL, Smalltalk, Logo, Basic. Like that, we have many programming languages. Okay, if we write any program within any programming language, this compiler, okay, within this particular programming, within this particular program, we will write some high level constructs. That's the reason we refer every program as a high level language. Okay, so this high level language is converted into a low level language. What is a low level language means? It's the mission language. Mission language in the sense, a language whatever a mission understand. What a mission can understand means, a mission can understand only two things. One is 0 and another one is 1. A mission can understand only two things. One is 0 and another one is 1. Okay. So 0 means there is no input. If there is 1 means there is some input. That is the meaning of 0 and 1. You take any mission, you take any computer, that can be the first computer, that can be the modern computer, that can be the future computer. Okay, you take a computer after 500 years. You take any computer, any mission that can understand only two things. One is 0 and the other one is 1. If you get the input as 0 means there is nothing, there is no input. 1 means there is some input. That is the meaning of 0 and 1. As we have only two things here, we even call a mission language as a binary language. Yeah. Binary means 2. Bi means 2. 0 or 1. That's the reason we refer this mission language as binary language also. Okay. So a compiler actually convert a high level language into a low level language. High level language means a language whatever we a program whatever we write with some high level constructs. So that can be, so already we discussed many programming languages. Okay, so this high level language will be converted into a low level language. Low level language means mission language, whatever a mission can understand. So this mission language will have two things. One is 0 and 1. 0 means there is no input. 1 means there is some input. So as it understands only two things, so a language with only two things, that's the reason we call a mission language as binary language also. So then, so what about flat and what about compiler design? Okay. So I think regarding this high level language, regarding any programming language. So regarding this programming, you take some courses like programming with problem solving, data structures. Okay, you take OOPS. Okay, you take some Java, you take some Python. Okay, you take some C++. You take some PPL, principles of programming languages. Okay, so regarding this high level language, okay, all these particular courses actually deal with how we write a program with this high level constructs. That's the reason, okay, regarding high level language, we have courses like C, PPS, that is programming with problem solving, data structures, OOPS, Java, Python, C++, principles of programming languages. All these particular courses actually deal with how to write a program with high level constructs. And regarding mission language, that is regarding binary language, We have courses like STLD, that is switching theory and logic design. We have DLD, that is digital logic design. These courses actually deal with how to go with binary language. So then what we deal with flat and what we deal with CD and what we deal with ATCD. So nothing but just in the definition we have a keyword saying that convert or conversion. What a compiler will do means a compiler will convert a high level language into a low level language. Okay, here we have a keyword saying convert or conversion. So this conversion is nothing but that is our course flat and CD. Here we don't discuss about any programming language, we don't discuss about any binary language, or we don't discuss about any machine language. We discuss about the conversion process. Our courses flat and CD or ACD, that is Automata and Compiler Design, deal with how a high level language is converted into a low level language. We deal with the conversion process. Yeah. So conversion of high level language to low level language. So this conversion, okay, so when we give a program for a compiler to compile, at that particular time the program with high level constructs, which is called the high level language, that will be converted into a low level language. During the conversion, so during this conversion, actually this conversion process actually split into some infinite number of languages. Okay, infinite number of languages. Okay, so how many languages you can have? You can have infinite number of languages. Infinite in the sense, we can't count. We can't count how many languages will actually come into existence. Okay, this conversion actually goes into a space which splits into some infinite number of languages. Okay, all these languages are actually defined with an alphabet sigma. Okay, during the conversion of high level language to low level language, this conversion actually goes into a space which actually splits into some infinite number of languages. All these languages are actually defined with sigma. Okay, so nothing but what happens here means, so during this conversion, what to say, from high level to low level, our language actually goes into some number of transitions. So the transitions can be some finite automata, that can be some regular languages. Okay, that can be some CFLs. Okay, that can be some CSLs or some PDA. Like that, our conversion process actually goes into some number of transitions. What is this finite automata? What is this regular language? What are these CSLs, context free languages? What are these context sensitive languages? What is this PDA, that is push down automata means? These are some number of transitions into which our conversion process actually undergoes. Okay, so during the conversion, so our high level language actually during the conversion, it goes into a space where the conversion process actually splits into some infinite number of languages. All these languages are actually defined with an alphabet sigma. This is mathematical representation of defining the languages. Okay, so nothing but, so and it goes to some number of transitions that can be finite automata, that can be regular language, that can be context free languages, that can be context sensitive languages, that can be BDA, and that can be LBA, linear bounded automata. So like that, what to say, this conversion process actually goes into some number of transitions and into some number of languages. Languages means that can be some infinite number of languages. So regarding these infinite number of languages, just now I discussed that this conversion process actually, during the conversion process actually, these high level languages they go into a space and they split into some number of languages, means infinite number of languages. These languages are called as automata languages, and we actually define these languages with some formal rules. All these are some formal languages. Formal languages in the sense we actually what to say, we define these languages with some rules and regulations. That's the reason we call them as formal languages. So what is flat means? Flat means formal languages and automata theory. Okay, formal languages and automata theory. Okay, simply we what to say, simply we term this one as flat. Okay, and this is also called as TOC, means theory of computation. Yeah, formal languages, languages whatever we define with some rules and regulations, and automata. Automata means what to say, it's a thing or a mission whatever works without human intervention. Okay, so we go with some theoretical content. So this automata actually work with some theoretical content, so we call automata theory. Automata means a thing or a mission whatever works without human intervention. Okay, similarly we even term this one as some theory of computation. Nothing but we try to compute the mission or these languages actually compute with some theory, which is automata theory. Okay, so first of all, regarding the introduction regarding flat. Okay, regarding the introduction regarding automata. Okay, this actually deals with how to write logics, how to write logics. Logics in the sense, simply I can tell you. Okay, simply I can discuss with some small example. Okay, for example, what to say, how we actually write some logics. For example, I will take a simple logic. Let me take an input string. Okay, an input string whatever ends with 1. Okay, the input string in the sense, here we represent our input string with the mission language, that is with the binary language, that can that is with the zeros and ones. Okay, so let me take a string. Okay, which is what to say, we represent that one with some mission language. Mission language in the sense the binary language. Okay, Nothing but let me take some examples. Okay, one is 0 1, the other one is 0 0 1, the other one is 0 1 0. Okay, 0 1 1. Okay, like that. Let me take a few strings. Okay, our logic is we need to identify the strings whatever ends with 1. Yeah, 0 1, this ends with 1. 0 0 1, yeah, this ends with 1. Okay, 0 1 0, so this don't end with 1. Okay, another one is 0 1 1, yeah, this also ends with 1. Okay, here we deal with how to write logics. Okay, so let me take what to say let me take a situation where what to say we are in a period where we work with a computer without a memory. Means let us take the first computer, our Charles Babbage computer. So the first computer actually don't have a memory. It is a what to say, it's a mechanical computer whatever takes some input, okay, which takes some mechanical input and which actually process that particular input and give us some output. Okay, it just actually our first computer is a mathematical calculator. It will do some simple calculations like addition, subtraction, multiplication, division, and with some logical operations like and or, like that. So let me take what to say, a situation where we have a computer with no memory. Let us take a computer what to say, which has no memory. Yeah, we have a mission, there is no memory, and we need to write some logics. Okay, so let me take the beginning of computers. Okay, the first computer don't have any memory, and let me take one more case where we have a mission with some simple stack memory. And let me take a mission with what to say, a tape memory. And let me take a mission with some what to say, unlimited memory. Just like our modern computer and the future computer. The last case is nothing but a mission with unlimited memory. That can be a modern computer or a future computer. So if we, okay, let us discuss how to write logics in these four cases. Okay, that is, in a case where we have a mission, there is where we have a mission without any memory, a mission with some simple stack memory, and a mission with some simple what to say, a mission with some tape memory, and a mission with some unlimited memory. So we'll try to discuss each and every case, how to write a logic with each case. Now let me take the first case. Okay, so now we have a mission just like our first computer. It's not our first computer, but just I am saying regarding the what to say, regarding its what to say, it's not regarding the Charles Babbage's first computer, but I'm just what to say, in order to explain what is happening, just I am taking an example as if our first computer. If you take our first computer, our first computer actually we don't have any memory. So like that we have a mission with no memory. So this just work like our first computer with no memory. If you don't have a memory means, then how you actually write the logic? So you take the same constraint. Okay, what is that first constraint? Just now I discussed. Okay, let us take we need to select the strings that ends with 1. Okay, we need to the constraint is nothing but we are given with some input strings. So once again, just let me clarify one thing. In mathematical, I think in mathematical subjects or in mathematical courses, if you take what to say uh, a string like this, they call this one as binary number. In few courses, in I think in in some mathematical courses and in some electronics and communication engineering courses, and in many courses they refer this particular input string as some binary number. But try to remember that in flat and CD or within ACD, we term this one as a we term this one as an input string. Input string. And never term it as binary number. Yeah, it's a binary number, but here we term that one as an input string. According to automata terms, we term it as we this is termed as an input string. It is not termed as a binary number. So an input string will have some set of input symbols. Generally within some courses they call input character, but we should not call them as characters, we should call them as input symbols. For example, 1 is an input symbol, 0 is an input symbol, another one is one more input symbol, 1 is one input symbol. Like that, we have totally 1, 2, 3, 4, 5, 6. We have totally some 6 input symbols within this particular input string. Okay. So once again, I am just clarifying the point. Within automata terms, we call this one as an input string and we never call it as binary number. So generally, I think in other courses, they call set of input characters, but we should not use a word called character. We call it as input symbol. Set of input symbols actually form an input string. Okay. So now let us come to the actual point. So here our constraint is nothing but we need to write some logics, okay, such that we will be given with some input strings and we need to identify the strings whatever ends with 1. The input symbol 1. Here what is our mission means nothing but our mission actually don't have any memory. Now we need to write the logic for a mission which don't have a memory. Now we need to think like a mission. So if we don't have a memory means, for example, let me take a simple keyboard, a binary keyboard. A binary keyboard. So it has only 2 buttons. One is 0 and 1. Okay. So let it actually. So we type a input string like this. 1 0 1 1 0 1 1. So we had taken a. So with our binary keyboard actually we typed we typed an input string 1 0 1 1 0 1 1. Okay. So now with the constraint we need to check whether this particular input string satisfies the constraint or not. Means what is our constraint means? We need to identify the strings whatever ends with 1. So here our mission don't have a memory. So in that case, how to deal such a mission means nothing but So now, so what we need to do means here, try to remember one thing, our machine actually don't have any memory. In that case, we don't have a memory means, for example, if our machine actually have some memory means nothing but, if we can store this particular input string means, this input string actually stores within the RAM, that is random access memory or the main memory. So here our machine actually don't have any memory. In that case, we can't store this particular input string. Then how to process this particular input string according to the constraint? So then how to deal this case means nothing but, we need to take the first input symbol. Yeah, let me take the first input symbol, that is 1. We need to process this one. Yeah, 1, it satisfies. Okay, next 1 0, no. Again, let me take the next number. So 1 0, next take the next number 0 1 0 1. Yeah, this satisfies. So now let me take the next number 1 0 1 1. Yeah, this also satisfies. Next one 1 0 1 1 0. Okay, no. Okay, so next 1 0 1 1 0 1. Okay, this also satisfies. Okay, so now let me take the last input symbol 1 0 1 1 0 1 1. Yeah, this satisfies 1 0 1 1 0 1 1. Yeah, this satisfies the given constraints. The given constraint is nothing but our input string, nothing but that need to end with 1. Yeah, so here so the number whatever given, okay, that satisfies the constraint. So that satisfies the logic, that is nothing but our input string need to end with 1. So once again I am just explaining the point. Here our machine actually don't have any memory. In that case, how to write the logic? Nothing but, let us assume that we have a binary keyboard which actually have only 2 buttons, one is 0 and the other one is 1. So it gives us an input string like this 1 0 1 1 0 1 1. So now what is the logic or constraint means, we need to identify whether the given string end with 1 or not. We need to check whether the given input string ends with 1 or not. So now, as our machine don't have any memory, so here for example, if our machine actually have some memory means, if we store this particular input string means, it's actually store within the RAM, that is within the random access memory, that is the main memory. As we don't have any memory, so here how to go with the logic means nothing but, we need to take every input symbol. Let me take the first input symbol 1. Yeah, we need to process means, we need to take the first input symbol 1, we need to process that. Next we need to take the next input symbol and we need to process that. Similarly, we need to take the third input symbol, that is 1, again we need to process that. Like that we need to process each and every input symbol. Why? Because here we don't have a memory. As we don't have a memory, we need to take every input symbol and we need to process. We need to take the next input symbol and we need to process that. So here, as we don't have any memory, we can't predict what input symbol we will get next. If we have some memory means, we can store that particular input symbol within that memory and we can predict what input symbol we will get next. For example, after 1 we are getting 0. If we have a memory means, we can know what input symbol we will get next, because this will be stored within that particular memory. As we don't have any memory, now we can't predict or we can't know what input symbol we will get next. First we got 1, we need to process that. Next we will get 0, we will process that. Next we will get 1, we need to process that. Like that, here as we don't have any memory, we can't predict what will happen, what input symbol we will get next. So now, so the first input symbol we got is 1. We processed that, yes. Here we have only one input symbol and that one input symbol itself is, that is the strings, yeah, that ends with 1, yeah. Next, the next input symbol is 0, yeah, 1 0, this don't end with 1, so it don't satisfy the logic. Next, 1 0 1, yeah, now the string actually ends with 1, this satisfies. Again, 1 0 1 1, yeah, this ends with 1. Next, 1 0 1 1 0, yeah, this actually what to say this actually don't end with 1, so it don't satisfy the logic. Again, 1 0, okay. Next, okay, sorry, yeah, 1 1 0 1, yeah, this satisfies the logic, yeah. Next, 1 0 1 1 0 1 1, yeah, it satisfies. Finally, okay, after this one, after this particular one, we don't have any input symbol. So from there, so by that, what to say, as what to say, so after processing 1 2 3 4 5 6 7, this seventh input symbol, this mission actually don't receive any input symbol. By that, okay, after processing the seventh input symbol here within the string, it don't get any input symbol. By that, the mission will understand that the string ends with this seventh input symbol 1. So finally, this input string actually ends with 1, so it satisfies the logic. So this is in the case where we have a mission with no memory. So now let me take the second case. What is the second case? The second case is nothing but if our mission actually have a simple stack memory. How to write a logic when our mission actually have a simple stack memory. So within a stack, yeah, we have a stack like this. Within our stack, we can make only two operations. We can perform only two operations. One is nothing but push, and the other one is pop. Here we have a memory which is a simple stack memory, and we can perform only two operations. One is push operation and the other one is pop operation. So now let me take the third case, that is nothing but when we have a tape memory. Let me take a simple tape memory. Now let us keep let us, as we have a tape memory, we can store our input symbol within this particular tape memory. 1 0 1 1 0 0 1 1 1. Okay, we just stored a tape memory. Here, when compared to the previous case, that is within the first case, that is a mission with no memory, when compared to that case, this case is somehow better. We are given with an input string. Okay, here we are given with an input string so that we can store that particular input string within this tape memory. So here this tape memory actually will have some number of memory cells. So within each memory cell we can store one input symbol. So here writing logics will become simple when compared to the first case. Why? Because here after storing the input symbol, okay, we actually start from here. Okay, nothing but we can process one and we can predict what will we can predict the so after processing the first input symbol 1, we can know what input symbol we will get next. So here simply we can know that the next input symbol is 0. So the next, after processing this one, we can easily know what will be the next input symbol, because we stored the input symbol within the tape memory. When compared to the first case, this case is very better. But here also we have some problems. What are those problems means? Here at a particular step, okay, we can move only one step forward or one step backward. For example, we want to go to some kth position. So if we want to go to some kth position, means let the kth position be somewhere around here. We have the kth position around somewhere here within the tape. Okay, we need to start. So what to say, here we need to, at a particular at a particular time we can go only one step forward or one step backward. Means at a particular step we can go, we can start from 1, we can go to 0, we can go to the next position, we can go to the next position, like that. We need to go up to k minus 1th position, then only we can go to kth position. So we, what to say, here some sequential movement is possible. Just like within our programming, what to say, we can't go to what to say, anywhere within the tape memory without, okay, here only sequential movement is possible. At a time we can move one step forward or one step backward. We can't simply move to a particular position within the tape. Like that, we have few problems with tape memory also. So yeah, so now let me take the same first case, that is a mission with no memory. So here now we need to write a logic in the form of a mission. So that is nothing but our mission actually don't have a memory. Okay, so what to say, our constraint or a logic is nothing but we need to identify the strings that ends with 1. So previously I think in the previously we are actually what is identifying the strings manually. So now let me discuss that one in the form of a let me what to say, construct the logic in the form of some mission which satisfies the logic. That is a mission whatever what to say, whatever accepts the input strings whatever ends with 1. So now we are constructing a mission, okay, with some states, okay, which actually work for the given logic. That is nothing but it will accepts the strings whatever ends with 1. Okay, it's a very simple logic. So nothing but we term that particular mission as finite automata, which is simply referred as FA. Finite automata. What is automata means? A mission actually works with a mission whatever works without human intervention. Automata means, okay, without any kind of human intervention it actually performs some operation. And finite means whatever have some meaning. Finite means whatever actually have some meaning. Finite automata means, finite means whatever have some meaning. Automata means whatever works without human intervention. Okay, before discussing about the definition of this particular finite automata, let me discuss a simple example. Let me take a string 10011. Okay, let me take an input string 10011. Okay, so now let me construct a simple finite automata for this particular simple input string. Okay, so a finite automata actually starts with an initial state. Okay, let me take that initial state as some q0. Okay, we represent an initial state like this. we represent within a finite automata. That can be a deterministic finite automata, or it can be a non-deterministic finite automata, or it can be a push down automata, or it can be a linear bounded automata. We represent within any automata, we represent the initial state in this form. Okay, we try to show that particular initial state q naught within a circle, and as it an initial state, we try to keep an arrow like this, arrow pointing to that particular state. Okay, so now what is the first input symbol here means 1. Okay, so now let the mission with this input symbol, let the mission move to the next state q1. So here try to remember that here each state is a kind of level. Okay, so here q0 and q1 are not different. Okay, they are the same state. Okay, q0 and q1 are same. Okay, they are same states. Okay, there is no difference between q0 and q1. The only difference is nothing but with the input symbol 1. Okay, that is with the first, within the given input string, with the first input symbol 1, our initial state q0 will move to q1. Okay, with the input symbol 1, actually q0 moves to q1. Okay, is that clear? So here q0 and q1 are not different, they are same state. It is the same state, but the thing is that it move from first level, initial level, to the next level. Just like you take a student, whoever studying first year B.Tech, you take some student like some Vikram or someone. Vikram in his first year he will be studying first B.Tech. Okay, after 1 year he will go to second year, after 1 year again he will go to third year, after the next year he will go to fourth year. Okay, so here Vikram, okay, when he joined B.Tech he will be in first year, next year he will go to second year, after, okay, the next year again from second year, for the next year he will go to third year, and from third year for the next year he will go to fourth year. So here the same student, actually he is changing his levels. Every year is just like a level. Here there is no difference between, the only difference here is nothing but in the first year, okay, Vikram is in first level. In the second year he will come to second level, in the third year he will come to third level, in fourth year he will come to fourth level. Like that, the same mission q0, okay, with input symbol 1 will go to the next level, which is termed as the next state q1. Okay, after that with the next input symbol 0, it again move to q0. Okay, it again move to q0. Okay, and what to say, and with the next input symbol 0, okay, here q0 will have a self move 0. Okay, what is this self move means? For example, let me explain what is this self move. For example, if we write a self move like this, okay, so the mission, it's a self move, nothing but the state action with some input symbol will move to itself, and it can move infinite number of times. Okay, for example, it can move once, okay, it can move 2 times, it can move 3 times. Okay, 1 1 2 3, like that it can move 3 times, like that it can move infinite number of times. A state, if it has a self move with some input symbol 1 or 0 or A or B, means with that particular input symbol it can move itself for infinite number of times. Okay, this self move is not a single move. Okay, this self move is not a single move, it can move multiple number of times, it can move, what to say, for infinite number of times also. Okay, so 1 okay, 0, okay, 0, okay. Next, from Q0 again with input symbol 1, it moved to itself. Yeah, it moved to itself. And let me keep a self move to Q1. Okay. So again we have two more input symbols 1 1. So 1 1. So a self move, with a self move a state can move multiple times, okay, to itself. So now let me check 1 0 0 1 1 1. Okay. So regarding the first input symbol, okay, our mission from initial state Q0, okay, it move to Q1 with the input symbol. Here mission from Q0 with input symbol 1 move to Q1 state, okay. The next input symbol is 0, again with the 0 input symbol 0 it moved to Q0, okay. So the next input symbol is 0. So here our Q0 will move itself. So here we have a self move, we kept a self move. So Q0 move to itself with input symbol 0, okay. Here we can, what to say, with Q, with self move a state can move multiple times to itself, but here as we have only what to say, already we completed one what to say, one move with 0. So here with self move Q0 actually move only once to itself. Next, it with input symbol 1 Q0 move to Q1, and we have a self move for Q1. So with this Q1, okay, with this 1 it will move to itself for twice. So the logic is satisfied. So here the logic ends here. So we try to treat this Q1 as final state. So try to remember that an initial state will be represented like this, okay, and a final state will be represented with a double circle. So we had taken a very simple input string 100 111, okay. So once again I am just explaining the finite automata. So with input symbol 1 Q0, okay, we are at the initial state Q0. So here mission with first input symbol 1 will move to Q1, and with the next input symbol it will again move to Q0. So after the next input symbol is okay, 1, this is satisfied, 0, this is satisfied, okay. The next the input symbol is one more 0. So 0 it moves only once, this self move actually it moves only once, mission moves only once, okay. 1, okay, this is satisfied. Again Q1 actually have a self move with this 1 2, it will move for 2 times. So this particular finite automata, this mission actually accepts any input stream that ends with 1. You can have an input string, what to say, with infinite number of input symbols. If it ends with 1 means definitely it will be accepted with this particular mission, okay. Let me take one more simple example for the same mission, okay. So let me take a an input symbol with more number of input symbols, just like 1 0 1 1 0 1 1 0 1 1 1, okay. So now let me take the first input symbol 1, okay, 1, next 0 0, next 1 1, next 1, okay, 1, okay, next 0, okay, next 1, next 1, next 0, okay, next 1, next 1, yeah, it's a self move 1, 1. Like that, you take an input string with with any number of input symbols. If it ends with 1 means this mission will accept that particular input symbol. So within finite automata we have two types of finite automatas. One is deterministic finite automata and the other one is non-deterministic finite automata. Okay, now let me discuss the types of finite automatas whatever we are having. So within finite automata we have two main types. One is deterministic finite automata DFA and the other one is non-deterministic finite automata NFA. And within non-deterministic finite automata we have one more type, that is NFA with epsilon moves. Okay. So regarding deterministic finite automata, deterministic means a finite automata or a mission whatever we can implement in real time. So deterministic finite automata means simply whatever we can determine. So whatever can be implemented in real time. So then what is NFA? NFA means non-deterministic finite automata. Means we can't implement a we can't implement this type of finite automata. A finite automata whatever we can't implement in real time comes under non-deterministic, means we can't determine that. Okay. So in order to identify some solutions for few logics, we actually go with NFA. So but in real time we can't implement a non-deterministic finite automata. And one more type type within NFA is NFA with epsilon moves. It even comes under NFA, but it will have an additional feature with epsilon moves. So regarding NFA or a DFA, what to say, it's a 5-tuple mission. Mathematically we represent that one as a 5-tuple mission. That is M is equal to capital Q sigma Q naught capital F delta. So what is Q means? Capital Q means it is finite set of states. So for the previous example we have few states. We represent every level of that particular mission with a particular state. So every state is a finite set of states. Finite means, already I discussed what is finite. Finite means whatever have some meaning. Okay, whatever is meaningful. Finite set of states means what some meaningful states. Okay, that is capital Q is equal to Q naught comma Q1. So the next one is regarding sigma. Sigma means it's alphabet. So here it comes under finite set of input symbols called as alphabets. So here in this case, in the previous example, we are defining every string with 0 and 1. So here our alphabet sigma is equal to 0 comma 1. Means within this particular language we represent every language with 0 or 1. 0 and 1. Okay. Next Q naught. Q naught means initial state. F capital F means final state. Okay. The next one is delta, that is mapping function. We can even call this one as transition function. So for the previous example, just mathematically we represent this one like this. Delta means, okay, delta transition. So capital Q, okay, with the sigma, okay, capital Q with the sigma goes to capital Q, means for the previous example I am just discussing, Q naught with input symbol 0 will move to Q naught. Here all states comes under finite set of states, that is capital Q. So Q naught with input symbol 0, that is sigma, finite set of input symbols. Q naught with 0 move to Q naught, and Q naught with input symbol 1 to Q naught with input symbol 1 move to Q1 state. Okay. So this is the transition state or transition function for the previous example. That is, okay, so already discussed, we represent within a finite automata, that can be anything, that can be NFA, DFA, NFA with epsilon transitions, that can be push down automata, that can be linear bounded automata, whatever that may be. We represent an initial state with this, with circle with an arrow pointing to it, and we represent a final state with double circle. Okay, sometimes your initial state can be your final state also. In that case, we represent like this. It means that this arrow represents that this particular state is initial state, and this double circle shows that it is final state 2. So for the previous example, Q0 with input symbol 0 move to Q0, Q0 with input symbol 1 move to Q1, Q1 with input symbol 0 move to Q0, and Q1 with input symbol 1 move to Q1. So regarding a solution for a finite automata can be the mission, whatever we construct, which satisfies the logic. And one more thing is, we can even represent the solution in the form of a transition table, that is with the transition function. So but in examination we need to write both. We need to write the mission and also the transition table.